Today we use Jordan form to prove that the sequence 1, 2, 3, 4, 5 is indeed counting. This is mathematically excessive, which is exactly why it is a good toy example. Civilization peaked at using Jordan blocks for kindergarten arithmetic. The sequence is defined by A1 equals 1, A2 equals 2, and AN equals 2 AN minus 1 minus AN minus 2 for n at least 3. The first few terms are 1, 2, 3, 4, 5, 6. We appear to have rediscovered counting, an achievement normally completed before shoelaces. But instead of guessing AN equals n, we will derive it by computing a matrix power using Jordan form. Package the recurrence into a two-dimensional state vector, AN on top, AN minus 1 on bottom. Then the recurrence says this state vector is the matrix A times the previous state vector. Here A is the 2 by 2 matrix with entries 2, -1, 1, 0, tiny matrix, suspicious amount of power. Iterating gives xn equals a to the n minus 2 times x2, where x2 is the column vector 2, 1. So the whole problem is now reduced to computing a high power of a. This is where Jordan form earns its lunch. Compute the characteristic polynomial of a. It is z squared minus 2z plus 1, which is z minus 1 squared. So the only eigenvalue is 1, repeated twice. That repeated root is the linear algebra equivalent of a warning label. Now a minus I is not 0, but its square is 0. So a is identity plus a non-zero nilpotent operator. That means a has a single Jordan block of size 2. Translation: this recurrence will produce a linear term, not just a constant. Counting has been located inside nilpotence. Nature is weird. Choose v1 equal to the column vector 1, 1. It is an eigenvector because a minus I sends it to 0. Choose v2 equal to the column vector 1, 0. Then a minus I sends v2 to v1. So v1, v2 is a Jordan chain basis. One vector stands still, the other falls into it. Very dramatic for two columns. In this basis, A sends v1 to v1 and sends v2 to v2 plus v1. Therefore the Jordan form is the block J with 1s on the diagonal and 1 above the diagonal. Let S be the change of basis matrix whose columns are v1 and v2. Then S inverse is the matrix 0, 1, 1, -1. Using the standard convention, A equals SJS inverse. Equivalently, if P equals S inverse, then A equals P inverse JP, which is the convention we will use for powers. Write J as I plus K, where K has 1 above the diagonal and K squared is 0. Then J to the K equals I plus KK, because all higher powers of K vanish. So J to the K is the matrix 1, K, 0, 1. Now compute xn equals A to the n minus 2x2, which becomes P inverse J to the n minus 2px2. The initial vector x2 is 2, 1. Multiplying by P gives 1, 1. Then J to the n minus 2 sends the vector 1, 1 to the vector n minus 1, 1. This is exactly where the n appears. It was hiding in the upper right entry of the Jordan power, like a tiny algebraic gremlin. Finally multiply by P inverse, which is S. The result is the state vector n, n minus 1. Since the top entry of xn is an, we get an equals n. Therefore the recurrence gives an equals n for every positive integer n. So yes, 1, 2, 3, 4 really continues as counting. Kindergarten was correct, but now it has a similarity transformation for emotional support. The point is not that this recurrence was hard. The point is that Jordan form turns repeated eigenvalues into explicit polynomial factors in powers of matrices. Main lesson. If A equals P inverse JP, then A to the K equals P inverse J to the KP. And Jordan blocks make J to the K easy to compute. Repeated eigenvalues are not just a technical annoyance. They create polynomial terms, like the n in this example. Mathematics, apparently, can count after all.